first talk in the afternoon, which is by Parthe Pandit, who's a Thakur Family Chair Assistant Professor with C-Minds at IIT Bombay. A brief intro about his career so far. He was a Simons postdoc fellow at UCSD and he got his PhD and MS degrees from UCLA, and prior to that he got his undergraduate degree from IIT Bombay, and he works on theoretical ML with intersections in signal processing and statistics. He was a recipient of the Smith Sciences AI 2050 Early Career Fellowships and Best ISIT Student Paper Award in 2019. So the speaker is definitely not fighting his sleep. Hopefully you can fight your sleep and pay attention, the English attention.
Thanks. Thanks for the kind introduction and for the warning to the listeners. First of all, it's a really exciting occasion, I think, a theory fest. And so I would like to congratulate IIT Madras for starting aRtCS. I had some really nice visits to the Simons Institute, and I'm hoping to I actually got several papers out of those visits to the Simons Institute, where I was just talking with someone on the board and someone else was passing by and they saw our problem and thought that they could solve it, and they did solve it, and we wrote a paper about it. Hopefully something like that can happen here as well. And yeah, so today I'm going to talk about some precise asymptotics of some high-dimensional statistical inverse problems. This is a tutorial style talk. I don't have any new results of my own that I'm presenting today. This is more of an overview of what's been done so far in a slightly different language that I find more convenient to understand these new techniques and frameworks that have been built in the last couple of decades. Okay, so here's the outline for my talk today. I'm going to talk about the linear inverse problem specifically. I'll start by presenting two optimization algorithms for solving this linear inverse problems, and they are loosely derived from some kind of a divide and conquer philosophy. I'll then show you a specific learning rate rule for those particular algorithms that enable us to analyze what happens in the algorithm in the system more generally in a statistical manner. So I'll make it precise what exactly I mean by statistical analysis of the optimization problem. And the analysis is going to be asymptotic average case analysis, and there again we'll see some kind of divide and conquer type of idea that shows up. So let's get started. We're going to talk about the statistical linear inverse problems. What's the problem? You're given some inputs and outputs. The inputs are these vectors AI, what we call features in machine learning, and the outputs are yi, what are called targets, or and what we're given is a statistical model for how this data may be generated. So yi is generated from some exponential family distribution that has this natural parameter AI transpose x, right? So x is this unknown parameter that holds across all the data points. Yeah. So I'm going to assume that x lies in n dimensions, and the number of samples that are given to me is m. Okay, so the popular approach to estimating this unknown vector x in this generalized linear model is some kind of a regularized version of maximum likelihood estimation. Turns out that in high dimensions there may be some problems with maximum likelihood estimation, and so in practice people usually do some kind of regularization. What is that? So you solve an optimization problem, the search is over Rn. The first term is some kind of a data fitting term. It measures how well you're fitting the data that has been provided to you, AI yi. And the second term is some kind of a structure enforcing term. It penalizes certain structures that you don't want in the solution that you propose. Okay, and then what's the kind of analysis that we are interested in? So suppose psi is some kind of a metric that measures some distortion between x hat I which is the ith coordinate of your estimator x hat, and x star I, which is the ith coordinate of some ground truth that may have generated your data, right? And we want to understand some average metric across the coordinates, right? So one standard thing we typically like to use is the mean squared error. This is in the 2 norm, but you could have other norms as well that you may choose to understand the behavior of this distortion depending on what the problem domain that you're working with is. Yeah? Okay. So we went over this already. The supervised learning problem and learning linear models in a supervised learning problem is essentially the same. The only difference there is that there you are interested in making predictions. So there the metric of interest is going to be some prediction error and not parameter estimation error. In machine learning, the most popular way of solving these kind of problems is through empirical risk minimization, or what is called structural risk minimization, when you add a penalty that sort of a regularization penalty. And in signal processing and statistics, the problem of sparse regression is also a sort of special case and a very well studied case of this problem. So you're given or you're not given this sparse vector x star that was generating the data, y is equal to a x star plus some noise. Yeah? A is your measurement that you know, y is the measurements that you obtained. So a is the measurement operator and y are the measurements. Yeah? And your solution is the solution to this optimization problem, again a least squares term plus some L1 penalty that encourages sparse solutions being proposed by the optimizer. Right? So this is the lasso problem that has been really well studied in statistics. And yeah, the challenge really in high dimensional statistics is we understand the behavior of these systems when m is much bigger than n. So m is the number of observations, n is the problem dimension that you're working with. But when that is not the case, understanding the behavior of the system is of interest more generally in this large class of problems. So let's look at a couple of divide and conquer style algorithms for solving these optimization problems. I'm going to rephrase the algorithms that are actually presented in their original papers in a manner that allows me to then use the learning rate rule that I'm going to talk about later. Yeah. So the optimization problem is essentially the following. You have this loss function here. I'm going to assume that all the elements of this loss function are the loss function is the same and the regularization function is also the same across all the coordinates. Yeah. And z is equal to ax. That's the constraint that ties the two terms in my objective function. Yeah. So this is one really interesting development in optimization and fast algorithms that has happened in the last 15 years or so, is the development of these proximal methods. So they solve the optimization problem by solving a certain scalar nonlinear optimization problem and using that to solve the vector optimization problem. Yeah. So what's the idea? You solve this particular scalar optimization problem. So the proximal operator of a function rho is defined as the minimization in R of lambda rho plus some quadratic penalty. Yeah, and the quadratic penalty is centered at u, which is the argument of this prox operator. Yeah. So this is a 1D optimization. It can be solved very efficiently, and there is a lot of work that has gone in developing libraries to solve these problems for specific functions rho. So this is a very nice library called proxop, or the proximity operator. This is my bookmarks don't show, but it's one of the first bookmarks on my browser page as well. I use it quite often. It's a very nice library. I like it. Okay. So you can use these libraries to solve the minimization problem. We'll see how we do that. So here is a particular first order optimization algorithm. It's called primal dual hybrid gradient. It was proposed by Chambol-Pock in 2011. So what they first do is they rewrite the original optimization problem as a saddle point problem. The only thing that's been done here is that The convex conjugate of L has been introduced. So L of Z has been written in terms of its convex conjugate. Yeah. And if we define the proximal operators for the conjugate L star and the proximal operator for rho, which is your penalty, you can write this particular alternate minimization approach to solve the problem. So what is this doing? You take two estimates, x1 and z0, and then you hold one of them fixed and you minimize the other, and then you hold the first one fixed and minimize the other one. So here you are minimizing over z, here you are minimizing over x, and you keep doing this alternatingly. Yeah. So there are two step size parameters, eta and gamma, that are introduced here. And the theory in the paper by Chambol and Pock shows that as the number of iterations of this algorithm grow, as t goes to infinity, the x and t together, x and z go together to the saddle point of this optimization problem, if the learning rates satisfy a certain bound. Yeah? Yeah?
Learning rates should be small,
Right,
right?
right. So these are reciprocals of learning rates. I've written them in that manner purposely because I'll be choosing specific values of gamma and eta later. So there is some sort of precision parameters, not learning rate parameters. Yeah? Okay. Here is a second order algorithm the reason I call it a second order algorithm is because it requires access to the singular value decomposition of the matrix A. So you write down the SVD as U, S, V transpose. U and V are both square matrices. U is a square matrix in m dimensions. V is a square matrix in n dimensions. And you rewrite the optimization problem in these transformed variables. So U and V are invertible matrices. So V transpose V is identity, U transpose U is identity. Yeah, they are unitaries. So you can write the optimization problem in this sort of transformed manner. Now, what are the sub problems that you can solve efficiently? So you can reduce this problem to this particular optimization problem. So you have minimization of some function of a rotated version of some vector w in m plus n dimensions. So w is just the concatenation of x and z, subject to some linear constraints, and those linear constraints are easy to. So this constraint here is an element wise operating constraint because it's a diagonal matrix. Right? So you can sort of project onto that constraint easily in some sense. Right? The subproblem structure is nice here because the proximal operator of a function composed with a unitary matrix has a closed form expression. So you can use this fact to design your fast algorithm. And that's exactly what this Piesman-Rashford splitting version of ADMM does. It initializes two dual variables, and it alternatively solves a proximal operator, and then it does a rotation, which is a transformation, then it does another proximal operator, and then it does the reverse transformation, which is Q transpose. Yeah. I call it pure because there is no damping involved. The original PRSM ADMM algorithm involves an additional damping step that is necessary to make it converge. Okay. And by converge again I mean that as t goes to infinity, the number of steps go to infinity, so w converges to the augmented Lagrangian of this minimization problem, which is equivalent to saying x and z converge to the augmented Lagrangian critical points. Yeah. This is all well and good. This is very classical optimization based analysis. We are going to do something slightly different today. Okay. So here is a quick contrast with the other optimization analysis that is very widely used. So the standard optimization theory typically focuses on worst case problem instances. Will the algorithm converge in the worst case problem instance that you are given? The AMP theory that we are going to see today is more of an average case analysis, and we'll make it precise what average case actually means. Optimization theory again typically works with fixed n and m. The problem dimensions are fixed, but the number of iterations are going to infinity. Yeah? What we are going to do here is we are going to fix t, the number of steps for which the algorithm is being run, but we are going to take n and m to infinity in some sense. Okay. And turns out that as you take n and m to infinity, you get some exact answers. You don't get bounds, you get exact limits. Limits exist and you can find out what those limits are. The problem with this type of analysis is that many times there are large universal constants which may not exactly tell you how well you are doing. What you see in experiments is different from what your theory actually tells you. So it gives you a very nice general understanding of the problem space and what would happen in the worst case scenario, but it doesn't tell you what would happen in a typical scenario that you would see, right? And so that's the AMP style theory is going to be very precise. It will give you precise phase transitions about when the problem is going to fail in this average case sense. Okay, let's quickly contrast with other type of statistical analysis as well. So the classical statistical analysis on this graph, the x-axis is the number of observations, the y-axis is the problem dimension n in which the search is happening. Yeah. So in classical statistics, you hold the problem dimension fixed and you take the number of observations to infinity. Right? In this regime, many nice results hold for optimization based estimators. Right? Maximum likelihood estimation is consistent under mild regularity conditions. You also have some kind of asymptotic normality properties for maximum likelihood estimation. Yeah. In contrast, information theory type analysis will deal with what are the hardest problem instances you can never solve. Yeah. Even in the average case. Yeah. There's a large amount of work that has gone in the last couple of decades in coming up with non-asymptotic analysis, which is what happens for a finite n and a finite m. Can you tell me exactly what is going to be the error if I run the algorithm? And this is a very powerful analysis, but again, it has large constants which sometimes are large enough that they don't give us precise insight into what's happening in the experiments that we run. And today we are going to look at this one regime in which we are going to work, which is that n and m are both going to infinity, but they're going to infinity at a proportional rate. So the ratio of n and m has a limit alpha, and that alpha is some constant. It's some number between 0 and infinity. It's not going to 0 or going to infinity as n and m go to infinity. Yeah. So there are some pros. The kind of theory that you get from this analysis is very actionable. Okay, I'll show you a trailer of what exactly actionable means. There are no large constants that are hidden behind big O notation. So whatever you see in practice is very well explained by the theory. The cons are that, well, the proportional regime may be restrictive and there are some assumptions on the data that you need to make under which this theory is going to give you precise analysis, but you may be willing to make those assumptions just because the analysis is so crisp. Okay, so here is the sort of the nature of the results that you can get using this theory. So this is the group lasso estimator or the multitask lasso estimator, which is solving this matrix valued optimization problem. So the search is over matrices of shape n by c. The first term is the Frobenius norm square. The second term is the sum of the two norms of the rows of x. Yeah. So the first term couples the rows of x, the second term couples the columns of x. So you can't solve this problem independently for the rows and columns. You have to solve it together. And suppose your data is actually coming from some kind of a ground truth solution x star, such that the ground truth solution has sparse rows. So very few rows in this matrix are actually non-zero. Okay. Then what I am showing you in the plot here, the dots are the results that I get in terms of mean squared error for an experiment that I ran for n equal to 600 and m equal to 720, where I am varying sparsity across the different colors. Yeah, those are the dots. The lines are given by exactly this function. What's happening in the limit when n and m go to infinity, but n over m is 600 by 720. Yeah. In this sort of regime, I am able to get an exact answer for what is going to be the limiting mean squared error of the solution. Yeah, it's in terms of some special functions which involves the sparsity, the signal power, the noise power, and some other special functions like the upper incomplete gamma function and the gamma function. The specific form of the function is not too important here, but what's interesting is that we can get exact answers to what is going to be the limiting performance of your estimator. Yeah, so the lines that are being drawn here are using this function here. Yeah, what is the x-axis? Sorry, I didn't mention what the x-axis was. The x-axis is the different values of the regularization parameter lambda. Yeah, so here clearly you can see a particular phase transition that all problems behave in a certain manner when lambda is large enough, and then depending on the sparsity there will be a bifurcation of the behavior of the system. No, second moments have to exist. Yeah. Okay, so here is an immediate application of this in a sense that it can be used in practice directly. A large amount of time is spent by engineers in doing hyperparameter tuning in practice. What this theory now gives me is an exact curve of what is going to be the best value of lambda for a given sparsity of the ground truth. Yeah. You may not know what the ground truth sparsity is, but if you have a sense of what that is, you can refine the search. So the y-axis here is in log scale. You can refine your search. You can also do something like back engineer what could be the sparsity based on what is the optimal value of lambda that you see in practice. Yeah? So these kind of levers you now have access to in some sense. Okay. So let's now sort of build some tooling to enable us to do this kind of analysis when we are working with these n and m limits going to infinity. So we are going to do analysis using again some kind of divide and conquer. We are going to break the problem down into two simpler subproblems for which we can give exact analysis, and then we will build on top of those exact analysis to get these closed form expressions for the limits that we want. Yeah, so the first problem is that of denoising when you are adding Gaussian noise. Okay. So suppose you have a scalar random variable x that has a density function fx that is proportional to e to the minus rho x. Yeah. What you observe is r, which is x plus some Gaussian noise with variance sigma. Okay. For this problem, the maximum a posteriori estimator, which is the mode of the posterior distribution p of x given z, is exactly what I have written here. It's the proximal operator of rho evaluated at r. Yeah, and the noise shows up somewhere there. Yeah. So this is one object that we'll use. We can analyze the asymptotics of scalar denoising quite well. We'll show exactly what happens. The other simpler subproblem that we can use is what is called ridge regression. Okay, so what is ridge regression? You solve this the quadratic optimization, but the penalty now is instead of L1 norm, we have the L2 norm squared. The advantage of this penalty is that there is a closed form expression for what is going to be the solution. Okay, so you can take the gradient, set it to 0, you get this closed form expression. And the nice thing is that again we can analyze what are going to be asymptotic properties of the ridge regression estimator. Okay, and then we'll combine these two analyses together to get what happens in more general nonlinear cases. Okay, so here is what the analysis for Gaussian denoising looks like. So suppose you are now looking at denoising a vector which has Gaussian noise added to it. So if your prior was the Laplacian prior, which corresponds to having rho of x is equal to the absolute value, the proximal operator you can find in closed form. It is what is called a soft thresholding operator, and it has certain thresholds that are given by the constants that exist in this, right? And turns out that if we assume that the empirical distribution of this vector x star converges to a scalar random variable x star, we'll maybe mention precisely what we mean by this assumption. We can exactly tell what is going to be the mean squared error of reconstruction. The limiting error of reconstruction is a two-dimensional integral over variables x and t. T has the Gaussian density and x has the law of whatever is x star. So dfx is a length element of x from the CDF of x. Yeah, and we're going to call this the function epsilon. We don't want to keep writing long integrals every now and then. Yeah. So g here is the proximal operator. Right. So there should have been a comma and gamma here, which I have missed. Yeah. So there's a gamma here in the notation, and that's gamma is the gamma that shows up there. It's related to the threshold. Yeah. Okay. So there's some spectral analysis that you can do for the ridge regression estimator. You can do some spectral analysis for the ridge regression estimator. This is a nice homework question to give to first year grad students or something like that. So you can write in closed form what is going to be the solution of your estimator, which allows you to actually open up what is going to be the mean squared error and write it in terms of the singular values of the matrix A and some other sort of transformed versions of the vector x star and the noise that is being added. Okay. And again, if you were to make this assumption that the empirical distribution of these three vectors converge to some three scalar random variables, you can again write down in closed form what is going to be the limiting mean squared error of this estimator. It's going to involve expectations of scalar random variables, and I'm just going to write this as an expression. I mean, there's not much I can say here at this point. I can just calculate these expectations in closed form because they are scalar random variables. Yeah, I can do this on a computer very cheaply. Yeah, this is a typo. It should have been x stars. Yeah. Okay, and turns out that these expressions show up again and again in all the analysis that we will do as well. So we call them the bias function and the variance function. And this is sort of the signal power and this is the noise power. So this is how it breaks down. Okay. Okay. So for matrices A, which are IID Gaussian. So if A is this matrix of size m by n, whose ijth element is drawn IID from a Gaussian distribution, and the variance is 1 over m, which is just done so that the normalization is not trivial. Then the distribution of the singular values behaves in a very predictable manner as the size of this matrix grows. Okay. So what I am showing you here is the histogram of the singular values squared of this matrix A, yeah, for n equal to 2048 and m equal to 4096. Yeah. And the limiting distribution only depends on whatever is the ratio of n and m. Yeah, this is what is called a Marchenko-Pastur distribution. It's a sort of celebrated result in random matrix theory, which shows up heavily in the kind of framework that we are going to work with. So we'll define this function t that shows up again and again. It's derived through something called the Steel-Chess transform of the distribution of the singular values squared, and the bias function is some algebraic manipulation of the t function, and the variance function is also another algebraic manipulation of the same t function. For the Marchenko-Pastur distribution, somebody has calculated exactly what is going to be this t function. So we know exactly for the Gaussian matrices what is going to be the behavior of the resulting error for the ridge regression estimator. Yeah, we know exact closed form expressions for how this is going to behave for different values of my regularization parameter lambda. Okay, so for the scalar denoising, scalar Gaussian denoising, we wrote it down as an expectation with respect to two variables. For the ridge regression, we wrote it down as an expectation with three variables: the signal, the noise, and something that was coming from the singular values of the matrix that we are using. So let's now use some kind of divide and conquer based analysis that puts these two pieces together and gives us closed form expressions for more general estimators. Okay, So here is a particular algorithm. It's called the generalized approximate message passing algorithm. It chooses specific values for these learning rates that showed up in the primal dual hybrid gradient algorithm. So this is a special case of the primal dual hybrid gradient that we talked about earlier, with a special learning rate that is chosen for the two updates. So gamma and eta have some special learning rates that have been chosen. Okay, it has the same fixed points as the primal dual hybrid gradient algorithm. Yeah, because we're only changing the learning rate and the learning rate rule, nothing else. So if we can say anything about limiting properties of solutions to this particular set of iterations, that will imply things about the behavior of the PDHG algorithm more generally. Yeah, and more generally also about the saddle point that these solutions are converging to. So we can characterize the problem more holistically. Why are these step sizes chosen in such a manner? Well, because some kind of decorrelation happens, and it allows us to get a tractable handle on what are the quantities these things are converging to as the problem size goes to infinity. So this is called generalized AMP because it generalizes the AMP algorithm, which was defined only for the square loss. So remember, H was the proximal operator for the conjugate of the loss function. The case of square loss was covered by Donohoe, Maleki and Montanari in a very nice paper from 2009. Okay, so let's formally state what this kind of convergence is going to look like. In order to state that convergence, I need to first define a new mode of convergence that you may not have seen before. So we are going to work with a class of test functions which are called pseudo-Lipschitz functions of order k greater than equal to 1. Okay. So what are they? Essentially, they're kind of relaxations of the Lipschitz function. The difference in the output is bounded by the difference in the input times something that is allowed to depend on what are the inputs. Okay. So for k equal to 1, this is just the class of Lipschitz function with Lipschitz constant 3. Yeah. But you are allowing k to be bigger than 1. So it's a generalization. So we are going to say that a sequence of random vectors, okay, so xn is my sequence of random vectors, xn is one random vector in Rn, and we say that it converges to this random variable x in this PLK sense if the following property holds. If for every pseudo-Lipschitz function, the average of this function over the elements of this coordinate, over the coordinates of this vector xn converge almost surely to the expectation of that same function with respect to x, which is what we are converging to. Okay. Why do we say almost surely here? Because x was a random vector, this empirical average is also a random variable, and so when we talk about convergences of random variables to constants, we have to qualify it with what is the mode in which this convergence is happening. We are going to talk about almost sure convergence here. Yeah. If you've seen Wasserstein metrics, this is equivalent to some kind of Wasserstein convergence. If you define the empirical CDF that you get from the coordinates of this vector xn, this is now a random CDF because the vector was a random vector, right? Then the Wasserstein distance between this empirical CDF and the limiting CDF is also a random variable, and that random variable converges to 0 almost surely. Yeah, so these are two equivalent ways of stating this notion of convergence. Okay, so here is the formal statement that we can provide for the analysis of this generalized approximate message passing algorithm. So here are some assumptions on the data that we are going to work with. So AMN is a matrix of size Mn. We already mentioned what are the entries, how are they distributed. We are going to assume that the ground truth converges in this PLK sense to X star. Yeah. Yes. So if it exists for if the kth moment exists, then it exists for all of them. So we just have to check for the kth moment, and we are implicitly saying here that the kth moment exists when we say this. Yeah. Yeah, so if the ground truth converges to some x star and the initialization also converges to some known random variable q1, then we can say something about the joint distribution of the iterates of this algorithm. Okay, so I run the algorithm for t steps, and I can say something about some iterates that show up in the algorithm. Okay, this is a formal statement. It has been proven rigorously. A corollary of this is what is actually useful for us. The corollary is the following: the mean squared error is exactly the error term that we saw earlier. Okay, what's different here is that gamma and tau are some sort of two constants that also we need to track. So these are scalars that we need to keep track of. Yeah. So what are these scalars? There is a clean recipe of how to come to these scalars after t iterations of the algorithm. The paper actually gives very precisely how to calculate what these scalars are going to be. Without going into too many details, they all essentially involve expectations of scalar random variables, integrals of at most 3 dimensions at any point. Yeah. You can get a very nice simplification for what happens in the case of the square loss, and I'll show you an experiment that validates the descriptions that were given by the theory. Okay, so the experiment that I'm going to show you is for the lasso problem, where the SNR is equal to 1, so 0 dB SNR. Sparsity is 1%, n, which is the input dimension, is 1024. Okay, for that particular scenario, what I'm showing you are the scalars that were showing up in the algorithm, the errors that were being presented by the iterates of the algorithm for different values of SNR. So the dots again are what you see by running an experiment on a finite dimensional problem. The solid lines are what you see are obtained by the scalar iteration that I wrote down. I know exactly in closed form what is going to be the value in the limit when n and m both go to infinity. You see some error bars in some of these terms. That's because the finite dimensional problem is still a random problem, and that is why there is going to be some variance to these quantities. And as you would expect, as the size of the problem increases, this variance shrinks. So this was for the problem with dimension 1000. The problem with dimension 4000 has much smaller error bars, and you can't even see the error bars in most of the places. Yeah. So this is a theory that tells you exactly what is going to be the behavior of the performance of the optimization formulation. Okay. So using this kind of theory, some very nice results have been derived for different problems in high dimensional statistics. I'm just going to share a couple of these results. So one such result was by Bayati and Montanari in 2011. They were able to show that there are some sort of implicit functions that tell us what is going to be the mean squared error, which is this quantity in red here, and how it depends on the regularization parameter lambda through some implicit function. Okay, so they didn't give me explicitly what was going to be the behavior of MSC as a function of lambda, but they gave it to me as an implicit function which involved 3 variables. That's good enough. Yeah. Okay. There is another experiment which essentially tells me that even if I were to run the primal dual hybrid gradient algorithm or this generalized AMP algorithm, they both find the same solution, and so their performance is asymptotically the same. What's interesting though is that the learning rate rule that GAMP uses is far below the threshold that the convergence analysis for PDHG requires, and yet somehow the algorithm also manages to converge with that particular step size rule. Yeah, it's kind of taking the entire spectrum into account and not the worst case directions that the worst case analysis was taking into account. So Gaussian matrices may be too restrictive an assumption to make, and we were able to do this kind of generalized analysis for arbitrary singular value distributions beyond Gaussian matrices in the case of ridge regression. So, can we do this for other problems as well? And turns out the answer is yes. There is a sort of variant of this machinery called the vector approximate message passing algorithm. This uses the second order algorithm that we talked about, the PRS ADMM algorithm, and it essentially uses these subproblems with their tractable analysis. Okay. Very quickly, here is a description of what the algorithm looks like. I am just stating what it's going to look like for the square loss case, but essentially for every other loss function you can reduce it down to exactly this form. But the algorithm is very symmetric in how it operates. There is a certain correction step that happens, and then you multiply by a unitary matrix. You apply a nonlinear operation that applies element wise. You do another correction, and then you apply the reverse of the unitary matrix. Okay, so it's very symmetric in how the algorithm operates. This makes the analysis very elegant in some sense. So again, the fixed points are critical points of the augmented Lagrangian, and here again we can give a formal analysis for what is going to be the performance of the algorithm as the problem size goes to infinity. So as n goes to infinity, if t is fixed, the number of iterations for which the algorithm is run, then we can precisely state what is going to be the limiting distribution for the iterates of the algorithm. And here again is sort of the closed form expressions for what are the errors that are incurred by the algorithm. And here you can see the two subproblems that we had broken it down into earlier show up. So there are two estimates of the solution, x and x hat, and their errors are being tracked through this scalar iteration. One involves this scalar integration with respect to the law of x star. The second involves the expressions that we got for the bias and variance for the ridge regression estimator. And you can show formally, specifically, that as you run the algorithm long enough, these two quantities match and they both go to what is the error of the estimator, that is the solution to the optimization problem. Okay. So a quick overview of what's the proof, what's actually allowing us to use so many Gaussians under the hood. Why are these things converging to Gaussians? So a very quick, this is a nice question again to ask in an intro to statistics class in grad school. So if Z is an isotropic Gaussian, and let D0 be the event that you have some linear measurements on Z, then the conditional distribution of Z given this D0 event is also a Gaussian with a mean that is given by T pseudo inverse B, and another independent Gaussian which determines what is going to be the covariance matrix for this distribution. Yeah. The interesting thing is, for Gaussians you can say that this is an independent copy of Z. Yeah. So a similar property also holds for matrices. So if A is a matrix whose entries are IID Gaussian, and you have some linear constraints on this matrix, so some constraints from the left, some constraints from the right, so these are two constraints, then if A is distributed IID Gaussian, then A conditioned on D1 intersection D2 is also a Gaussian matrix with a mean that has an expression and a covariance that comes from another independent copy of a Gaussian. Okay. Turns out that this property can be extended beyond the space of Gaussian matrices. We can apply this to what are called Haar distributed matrices. Haar distribution is the uniform distribution on unitary matrices of any size, right? So, if we have the event is A is equal to VB, A and B are deterministic in this particular slide, then conditioned on this linear constraint event, the distribution of V is, again, you can break it down as a deterministic part and a random part. And the interesting thing is that the random part is always going to remain independent of the deterministic part. Yeah. Okay. So the proof essentially is so till the tth iteration, the algorithm has seen certain times the matrix, the random matrix V has been multiplied certain times from the left and certain times from the right. This gives some linear constraints on what is the randomness that remains in this random matrix, right? So this gives a conditional distribution for the random matrix after t iterations of this algorithm, and that allows us to show that certain iterates of the algorithm can be expressed as some deterministic term plus a term that behaves like an independent Gaussian. Yeah. So here is sort of the pictorial description of what's happening. So on top is the behavior of the algorithm. On the bottom is the equivalent system of scalar random variables and how you can derive this system. So every time the algorithm hits a unitary matrix, you are going to get some kind of Gaussianizing behavior on the output, right? What that means is everything that you want to track in the algorithm is essentially a Gaussian or some nonlinear function of a Gaussian. And how do you keep track of Gaussians? You only need to keep track of their means and covariances, and that's what the state evolution machinery does. It just keeps track of what are the covariances that are involved in the algorithm. Okay, so here are some examples of what kind of results have come up in the last few years using this kind of machinery. So here is one result. This is a very nice result from a paper that came in NeurIPS in 2020. So they talked about the phase diagram of the true positives and the false discoveries that you get when you use the lasso formulation to find support recovery type of problems. And as you change the level of sparsity or the level of hardness of the problem, you see different behaviors and you see some kind of phase transitions show up in what is achievable and what is not achievable. Yeah. So these kind of phase transitions you can exactly characterize using this framework to do your analysis. Yeah, and this machinery has been applied quite widely in studying the behavior of many problems in high dimensional statistics now. Yeah. So TPP is the true positive proportion and FDP is false discovery proportion. Yeah, and yeah, so yeah. Okay, here is another very nice paper that came out in 2022 in Annals of Statistics on the surprises in high dimensional ridgeless least squares interpolation. So this is a phenomenon that is recent to machine learning as well. It's called the double descent phenomenon. So as you increase the ratio of n over m, you see that the system's performance first degrades, you do some kind of overfitting, and then somehow strangely the error in your system reduces again. And they use this machinery to get some very crisp analyses. So here again in these plots, the dots are what you get from experiments and the lines are what you get from these closed form expressions from the analysis. And turns out that this property of double descent is very much dependent on what is the level of regularization that you use in practice. As you tune the level of regularization, you get these different curves with different colors. Yeah, so at some point the double descent just goes away if you optimally tune your regularization lambda. Okay. They didn't quite use exactly the same machinery. It was more based on ideas from random matrix theory, but it's only slightly different from the machinery that was developed. In fact, Andre Montanari was the one who wrote the first paper on these AMP type analyses. Okay, yeah, so this is my last slide. I'll just quickly summarize what we talked about. We were able to do some kind of average case asymptotic analysis for optimization problems using closed form expressions. and this allows us to actually pose and answer some very important and interesting questions in statistics, machine learning, signal processing, and so on. And this enables characterizing sort of phase transitions in these systems, which is very important in today's day of sort of doing theory research, where a lot of phenomena are coming to us from sort of the empirical world. The nice thing is that this entire framework is sort of full of rigorous proofs. There's no hand wavy arguments here. And there are sort of some other equivalent frameworks that are also being developed simultaneously, and we don't fully understand the connections between these frameworks, so there are some open gaps there as well. This framework has been used quite widely in the last 5 years to understand many complex behaviors that arise in systems involving deep neural networks. So things like test time inference and scaling laws analysis have also been done using this kind of a machinery. Yeah, with that I'll stop. Thanks.
Questions? Okay, since there are no questions, I'll ask one.
Okay.
Yeah, so one thing is like you are trying to write down a precise characterization of an asymptotic mean square error. Is there a way to use that to design better algorithms? Like,
Yes, yeah, you can use this information to design better algorithms.
but there'll be unknown quantities and all that, right? Yeah.
Yeah, so these won't be sort of algorithms that would work in the worst case scenario.
Not worst case, but even on an average, like you have a data set and you had the matrix and maybe something about the ground truth that you don't know.
Right. So you can use this information to design better algorithms. Yes. Yeah. Yeah.
I mean that part is like, is it unexplored? Because okay, I get an expression.
I don't think it's been explored. Well, there is some limited work on. So there is this class of algorithms which are called unfolding based methods for solving inverse problems. So they essentially roll out this gradient descent iteration, which involves a large number of matrix multiplications, and then they say, well, we'll throw out whatever the original matrices were. We'll just learn these matrices by throwing some data at them. Right. So this is so you can do more efficient unfolding in some sense. You can reduce the depth of whatever unfolding you're doing using some problem structure that you may know extra.
Or to put it differently, like is there some way I can use that expression to come up with an algorithm which gives me lower asymptotic mean square error? Okay, this is.
Oh, this is actually to do with the saddle point, right? Like it's if any algorithm reaches that saddle point,
that's enough.
You are going to get that same error in some sense.
Okay, so that's.
So
that's
what does better algorithm then mean is
yeah, I need to think about it. But like you have a mean square error for every like x hat.
Yeah.
Okay, my better is always in non-asymptotic. Asymptotic, I don't know. But like
yeah.
For every non-asymptotic case, if I have a like a mean square error bound, I can use it to see if I can come up with a better algorithm with a lower bound. But in the asymptotic regime, I don't have a clear direction.
Yeah. That's an interesting question. I'll think more about this.
It's still brainstorming. Yeah. So yeah, thanks.
Yeah.
Thank you. Maybe potentially unrelated, but so in these, do you expect, does this framework also give you, let's say, rates of convergence, right, under some assumptions, good assumptions on the data, right? So the context behind this is at some point there was an algorithm which I was looking at which got, in theory we could only show like in the worst case setting some polynomial rates, but in all empirical examples we looked at it converged linearly.
Yeah.
Right. So I wonder if something like this can.
Yeah, something like this does hold actually here. So in this algorithm you can show will converge exponentially fast if it converges.
Okay.
Because there's no guarantee of convergence. So this is kind of a more of a proof technique. So you would still use something like PDHG or ADMM to actually solve the problem. But once you've solved the problem, you still want a handle on, well, could I have done better by tuning lambda or something like that, right? Those kind of questions are just hard to answer without doing them by yourself. This kind of gives you a handle on these kind of quantities. How would the behavior of the solution that PDHG finds, can you give me a handle on that in terms of the other hyperparameters in the problem? But yeah, if the algorithm converges, it converges much faster than any other algorithm I have seen. That it converges is, there's no guarantee for that. Like, yeah.
Thanks.
Thanks.
In that case, there are no other further questions. Let's thank the speaker again. And you want to give it? Yeah. Okay. As a token of appreciation, I think you get a memento.